So this is the last one from the separable differential equations homework, and the final result you ended up with was, I believe, is this right? Y equals the square root of x squared plus tangent x plus 25, correct?
Yes, there might be a negative in front of the square root, though.
Oh, there's a negative. That's not going to affect our interval of validity, so but we'll put it there anyway. So we're looking for the interval of validity is what we need here, and so we have two different things going on here that can cause restrictions on the domain of this function. One is the tangent x, right? Tangent x is undefined at some certain values, right? It's undefined at positive or negative pi over 2, positive or negative 3 pi over 2, 5 pi over 2, 7 pi over 2, and so on. Right, so we know that those are values at which we're undefined. So that's the first thing. Second thing is that what's inside of here must be 25, must be greater than or equal to 0, right? So we can't take the square root of anything that's negative. So we got to figure out when that particular function is positive. And since that's not something that we can do real easily without a calculator, I mean, we could like approximate the x-intercept using Newton's method, but that's not necessary. We'll just graph that function, and we'll do it on Desmos here. X squared plus tangent x plus 25 is that function that's inside of there. And so we're interested in when is this greater than 0? Well, and we had, sorry, what was our initial condition? That x was equal to 0, right?
Yeah.
Yeah, so when x is 0, the left-hand piece of that that's positive is from negative 1.534. And so that's how I got that value of negative 1.534. And then it's still positive, you know, all the way up here until we get to our asymptote of pi over 2, it would appear, right? Because we should be approaching that asymptote of pi over 2 before we drop back down here to go above pi over 2 and hit this next x-intercept on our other function, right, on this x squared plus tangent x. This is to the right of pi over 2, so it should be in the next section over. And so our interval should be negative 1.534, inclusive of that point to infinity, or to pi over 2. Does that make sense?
Yeah, it was helpful to see that again. Thanks.
Yeah, and like I said, you won't have to do that on the AP test or on the quiz with the calculator. They'll all be fairly straightforward ones that you should just algebraically be able to solve. But good to see the concept there. Any other questions on any of the separable differential equation stuff before we start talking about area again? All right, so I believe this was the next area problem that we were about to start talking about. Is that true?
Oh, well, we haven't done this one yet, so probably.
Yeah, we did this one, right? We did x squared minus 2x minus 3.
Yeah.
Okay. All right, so let's look at this one. We want to find the area of the regions between sine x, cosine x from x equals 0 to x equals pi. So now chances are we probably don't know exactly what that function looks like. We could use Desmos to graph it, but let's see if we can figure out a way to do it without graphing it. And we'll check our graph to make sure that what we're doing is correct a little bit. So how do we go about this if we don't know what it looks like? We know that it might sometimes be above the x-axis and might sometimes be below the x-axis. So we need to figure out if it ever crosses through the x-axis. So how do we determine that for a function?
Set it equal to 0.
Set it equal to 0. Good. So we'll take sine x, cosine x, and set it equal to 0. Since that's a product of two different things, the 0 product property says set them each equal to 0. And what does that give us? It gives us x equals 0 and pi for this, and x equals pi over 2 for this. I'm only looking on the interval from 0 to pi. So those are the only three values we get between 0 and pi, including 0 and pi. Well, since these are our endpoints, we're less concerned about these. We know it might cross through at pi over 2. So if I made a sine chart here, I could find whether my function sine x cosine x is positive or negative between 0 and pi over 2, and whether it's positive or negative between pi over 2 and pi. We know if it's positive or negative anywhere on the interval between 0 and pi over 2, it's positive or negative on that entire interval, right? And if it's positive here, it's always positive on that full interval, right? Because there's no other x-intercepts. So if we plug in, let's say, pi over 4, the sine of pi over 4 is positive, right? True?
True.
And the cosine of pi over 4 is positive. So we got a positive times a positive, which equals a positive. So everywhere on the interval from 0 to pi over 2, we know our function is positive. It's above the x-axis. And what about between pi over 2 and pi? If we plug in something like 3 pi over 4. What do we get?
Positive times a negative.
Positive times a negative, which should give us a negative, which tells us that our function is below the x-axis. So we're going to have to break this down into two different integrals, right? One will be the integral from 0 to pi over 2 of sine x cosine x dx. And the other one will be the integral from pi over 2 to pi of sine x cosine x. But instead of adding these two things together, I have to subtract the second one because the second one will come out to be a negative value. Everybody good with that?
Yep.
Okay. And if we wanted to, we could go back here to Desmos and say, just make sure that our work was right, sine x cosine x. And if we're talking from 0 to pi, sure looks like we were right. From 0 to pi over 2, we were above the x-axis, and from pi over 2 to pi, we were below the x-axis. So our algebra there was correct. So how do we integrate sine x times cosine x?
Should we do like a u substitution?
We should. We're going to have to do it for both of them, right? We're going to let u equal sine x, so that du will become cosine x dx. And we're going to end up with an integral of u du minus another integral of u du. And when we convert all the functions to terms of u, we have to convert all of our limits of integration to terms of u. So what's the sine of 0?
0.
And the sine of pi over 2?
1.
1.
And again, the sine of pi over 2 is 1, and then the sine of pi is 0. And so this becomes sort of an interesting little thing here. We've got the integral from 0 to 1 of u du minus the integral from 1 to 0 of u du. And I could do each of these separately if I wanted to, or if we wanted to be, I don't know, smart about it, we don't have to do it this way. We could use the rule that we can flip the limits of integration and flip the sign. Remember doing that a while back?
Yeah.
So we could just get this, and that would be equivalent to two of those integrals. Like one integral from 0 to 1 of u du should be equal to, or if we add another one to it, should be equal to 2 integrals from 0 to 1 of u du. Good or no? which should be 2
Good.
times u squared over 2 from 0 to 1, which ought to be 2 times a half minus 0, or 1 unit squared. Easy enough or no?
Yeah, that was good.
Yeah.
All right, somebody is asking me to go back, so I'll go back here for just a second. All right. Any other questions on that one before we move on to some other very cool stuff that you may or may not think is very cool, but I do? All right. Let's think, in fact, let's just make a new page here. Let's just see if my laptop will give me the toolbar for this so I can have different colors for this thing that I want different colors for. Doesn't look like it. Perfect. Okay. So, oh, now it did. Great. Here's some function, f of x. Here's some other function, g of x. Here's a, here's b. I want to know this area, the area between f of x and g of x from a to b. How am I going to find that area?
Do the integral of f of x from a to b minus the integral of g of x from a to b.
Right. If I did the integral of f from a to b, that should give me all of this space also, right? But if I subtract the integral from a to b of g, it should take off all of that, right? And so it should just give me the space between f of g. So the area between f and g should be the integral from a to b of f of x dx minus the integral from a to b of g of x dx, which if we wanted to, could be combined together into one integral to say the integral from a to b of f of x minus g of x dx. You all agree with that?
Yeah.
All right. Now, this is all good and fine if both of my functions are above the x-axis, which they are. True? What if they're not? Let's suppose that f of x is above the x-axis and g of x is below the x-axis. And I want the area between them from A to B. Is that same formula going to work, or do I need to adjust it because something's below the x-axis?
It should work because you're like subtracting a negative. Which
Exactly.
just means you're adding.
Right, so the red should be my integral from A to B of f of x, right? That's all of this section that's above the x-axis. And if I subtract the integral, maybe I'll do this in a different color. If I subtract the integral from A to B of g of x dx, that's this, which the integral is negative because it's all below the x-axis. That should then show me that I get minus a negative, which should give me this, still give me the total area. Everybody see that? Or no?
Can you explain that again?
Yeah, so the integral from A to B of f is a positive value, right? And that gives me everything below the curve and above the x-axis. The section in blue down here is the integral itself is negative, right? Because when I take the integral from a to b of something that's below the x-axis, that number comes out to be negative. It's the opposite of what this area is. And so if I still subtract f minus g, I'm now subtracting a negative number, which makes that a positive. Makes this, f, the value of the area of f plus the area of g. And they get combined together to give me the full area between the two functions. Does that make sense or no?
Yeah, thanks.
Mm-hmm. Everybody good there or no? All right, that's all great if f is always above the x-axis and g is always below the x-axis. But what if it's not always above or always below? Suppose there's f and suppose there's g, and I'm going, we'll say from a to b, and here's f and here's g. I guess I should extend that further. And I still want the area between these two functions. All right, I still want to get this area. Can I still just do the integral from a to b of f of x minus g of x dx?
I don't think you can because it's like crossing the x-axis, like your integrals. Don't you have to like separate it when it's
Let's
crossing the
investigate
x-axis?
and see. Let's take a look at where the first one crosses through the x-axis. Right, so like, and let's actually make a mark here. Right, I know that this piece, where this one was always above and this one was always below, we already dealt with that, right? And so that's okay, true? Isn't it? That's what we just did here.
Yeah.
One's always above, the other's always below. And then this one, where they're both always above, we just did that, right? Right here. So this one's okay. And so the only question here is this one. And so for this one, if I'm doing f, the upper one, minus g, the lower one, what's the integral of f give me? It gives me this blue as a negative value. So let's call this thing here, the value of this, let's call it m. Okay. And then it also gives us, when we do g, it gives us all of this, right? This green and this blue, all as a negative. So let's call this bigger section here n. It's going to give us this little negative, which is m, minus this bigger negative, which is n. And let's define this even further here. So let's say n is the green and the blue in that interval, but let's call p just the green part. So how can I rewrite n? N should be equal to what? Should be equal to p plus m, true?
Yeah.
And so what we're effectively doing is we are doing m minus the quantity p plus m. So first off, m minus m should cancel out, right? It just gives us the opposite of p. Well, p is negative, isn't it? Since the integral down there was negative.
Yeah.
So what's the opposite of p? It's just this green as a positive. So this is still okay. So it doesn't matter if we cross through the x-axis. It doesn't matter if both of them are above, both of them are below, if they cross through in the middle of the interval. Anytime we are doing the area between two curves, all we have to do is take the upper one minus the lower one and integrate. Now, if we have a situation where the two curves intersect between A and B, where we have multiple different regions that we're talking about, this is when we would have to separate it into two different integrals. Right, we'd have to find this value C, and we'd have to integrate from A to C, the upper minus the lower, and add that from C to B, the upper minus the lower, which in this case becomes G minus. Does everybody see that?
So even though it, on the last one, like it intersected the x-axis, like that doesn't matter. You can just still do the standard equation that we derived.
Correct. Exactly. The only thing that will affect it is if the two functions cross through each other on the interval, as in on your interval, the same function is not always the upper function of the region. Sometimes it's f and sometimes it's g. Does that make sense?
Yeah.
Okay, cool. So that's our intro to finding the area between curves. Here's the formula, right? As long as f of x is always greater than or equal to g of x on the interval, the area between them should be the integral from a to b of f minus g, which is what we just said. It holds true for any such case where f is greater than or equal to g. And so, like we said, the only stipulation there is if they cross through each other, that means that f is not always greater than or equal to g, and we have to split it up into the multiple intervals. All good? I hope. All right.
Yeah.
So let's see if we can find the area between these two functions, x squared plus 1 and negative x squared minus 1. So here is x squared plus 1, and here is negative x squared minus 1. And we are just looking between 0 and 1. So we are interested in the area of this region right here. And is one function always above the other function on that entire interval?
Yes.
Yep. Which one is always above the other one?
X squared plus 1.
So we will do the integral from 0 to 1 of x squared plus 1 minus, and make sure you put your second function in parentheses, so minus negative x squared minus 1 dx, which will give us the integral from 0 to 1 of x squared plus x squared, so 2x squared, and 1 minus negative 1, or plus 2. Everybody good with that setup? I hope.
Yeah.
Okay. So now we'll just do the integration. 2x squared becomes 2/3 x cubed, plus 2 becomes plus 2x. 0 to 1. And we'll evaluate. 2/3 of 1 cubed is just 2/3 plus 2. And then minus 0 plus 0. 2/3 plus 2 is what?
2 2/3.
2/3, yes. Which, please don't ever write things as mixed numbers,
Why not?
because they're awful to look at and it makes things confusing and they look horrible and they're the worst thing in the world after decimals. Always use improper fractions. Every teacher you've ever had since like 2nd grade when you first learned what a fraction was should have told you use improper fractions. They probably didn't, but they should have. Any questions on that one? All right, let's do another one. Let's find the area between secant squared x and sine x, between 0 and pi over 4. So I think the first thing that we might want to do here is sketch a quick graph. We know what sine x looks like, right? It starts here and looks like this. Here's pi over 2. So here should be pi over 4. That one should be easy, right? Y equals sine x. We may not know as well what secant squared x looks like, though, between 0 and pi over 4 at least. So first off, what is the secant of 0?
One.
Secant of 0 is 1, so secant squared of 0 is, I don't know why I put theta there instead of, secant squared of 0 is also 1. So we know sine hits a max of 1, so that's 1. And then we know that secant, right? Secant is 1 over cosine, right? Well, what's the cosine function doing? The cosine function starts doing this, right? Going down. And so if I'm doing 1 divided by some number that's between 0 and 1, that should tell me what secant is doing.
Yeah.
What should secant be doing?
It's going to be a lot bigger than sine x, y equals sine x.
Right, it's going to be increasing, right? In fact, when cosine is 0, 1 over that 0 would be infinity, right? Which should tell us that
We're asymptoting.
we actually have an asymptote up here, and that secant, or secant squared for that matter, is going up towards an asymptote at pi over 2. And so that should make it pretty evident to us that between 0 and pi over 4, secant squared is always above sine x. Do y'all agree?
Yeah.
Okay. So that's the sort of analysis you should be able to do without a calculator to determine which one is above the other one. So we're going to integrate from 0 to pi over 4. The upper function, secant squared x, minus the lower function sine x dx. And what's the integral of secant squared?
Tangent x.
Tangent x. And what's the integral of negative sine x?
Cosine x.
It'd be positive cosine x. And we're going to evaluate those from 0 to pi over 4. And what's the tangent of pi over 4?
1.
And cosine of pi over 4 should be root 2 over 2. And we're going to subtract tangent of 0 plus cosine of 0. And what's the cosine of 0?
1.
1. So it looks like we got 1 plus root 2 over 2 minus 1, which will just be root 2 over 2 units squared. Good or no?
Good.
Great. All right. Let's see if we can find the area of the region enclosed by this parabola and this line. So what's different about this one?
We aren't given like 2x values.
Right. If we look up here, we were given x equals 0 to x equals pi over 4, x equals 0 to x equals 1, right? Here we don't have that. We just say find the area of the region enclosed by them. So let's sketch the graph first. 2 minus x squared. What does that look like? It's got a y-intercept of 2, and it's just, that looks horrible. And it's just a parabola that goes down, right? Like that. That's
Yeah.
y equals equals 2 minus x squared, basically. And what about y equals negative x? It's just a line, right? Just like that. And so that should give us an indication of what this region looks like. Right? It's this region right here where they're intersecting. And so in order to figure out the limits of integration, we're going to have to do some algebra on our own. So how do we determine where two functions intersect with each other?
Systems of equation.
Yeah, system of equations, right? And they both are set equal to y, right? Y equals this and y equals this. So I should just be able to set 2 minus x squared equal to negative x. And if this was the AP test, they want to see you setting them equal to each other and solving to find those limits of integration. So that would tell me that x squared minus x minus 2 equals 0. And we should be able to factor that and solve it, right? And that should factor to x minus 2 and x plus 1, telling us that those two functions intersect each other at x equals 2 and at x equals negative 1. And on the entire interval, right, one function is always above the other one. So we should be able to write this out as an integral from negative 1 to 2 of the upper function, which is our parabola, minus our lower function, which is the linear one. Everybody feel good about that?
Yeah.
Yep.
Great. All right, so let's integrate. 2 becomes what?
2x.
Negative x squared becomes negative x cubed over 3, and then minus negative x is plus x, right? And that becomes plus x squared over 2. And we'll look at this from negative 1 to 2. So that ought to give us 4 minus 8/3 plus 2 minus negative 2 plus 8/3, or sorry, plus 1/3. That's not a negative 2. Plus 1/3, and then plus 1/2. And what does that come out to be? 4 plus a 2 is 6, plus another 2 is 8, right? Yeah, 8 minus 8/3 minus another third, so minus 9/3, and then minus 1/2. So 5 minus 1/2 should be 9/2 units. Any questions there? Everybody good with that?
Looks good.
All right, let's do this one. Let's see if we can find the area of the region enclosed by y equals 2 cosine x and y equals x squared minus 1. So first, let's graph these. X squared minus 1 looks like this, right? And 2 cosine x looks something like this. True?
Yep.
Yeah. Okay. Is one function always above the other function for our region?
Yep.
Yes.
So it should be an integral of the upper one, which was 2 cosine x, minus x squared minus 1 dx. But we still need to figure out where those intersect. And we do that by setting them equal to each other, right? So 2 cosine x equals x squared minus 1. But if we do that, that's an equation that's a little bit difficult to solve, isn't it?
Yeah.
Yeah.
Yeah. So we'll use our graphing calculators to solve that. On your graphing calculator, just graph both functions. One option is to graph both functions and use the intersect function on your graphing calculator and then like second calculate trace thing. The other option would be to do x squared minus 1 minus 2 cosine x and just look for the x-intercepts of it. And what I'm going to do is just put them into decimals. 2 cosine x and what's x squared minus 1. And we'll see that they intersect at negative 1.265 and positive 1.265. Everybody agree there?
So on the graphing calculator, how would you, like I hit the intersect thing, like what do you do after that?
All right, so if you do second calculate intersect, what you do is you pick a point to the left of where they intersect. And then it's
Does
like,
it matter that there's two intersections or no?
well, I mean, you're going to have to find both of them.
Okay.
I mean, you can see that they're plus or minus here, and you know that they're both equivalent to each other just based on the fact that both of these are even functions. Right, they're both symmetric across the y-axis. X squared minus 1 and 2 cosine x are both symmetric. So one is just the opposite of the other. But what you do is you pick a point that's to the left of one of the intersection points, hit enter on it, and then scroll to the right until you're to the right of that intersection point. Hit
Okay.
enter again. And then it'll say guess after that. And then after it says guess, hit enter a third time.
Okay, cool, thanks.
And what is the value? And we're gonna do all that stuff once I get my graphing calculator on my computer to work again. What did it give you here? To more than 3 decimals.
I got 1.265424.
265,424. Okay. So normally, if you're using a calculator on the AP test, you do not want to round your values until you get to your final answer. So the final answer is this actual integral. And since we are, we're gonna have to evaluate it at these pretty awful looking decimal values, we might as well just use the graphing calculator to do the integral and all of that for us. So I'll have you guys use math option 9 on your graphing calculator. Plug this in as your lower limit, plug this in as your upper limit, put in the function. If you'd like to distribute the minus sign through and just type in 2 cosine x minus x squared plus 1, that'd be great. Or you can type it with the extra parentheses if you want. But I found that sometimes the extra parentheses within the integrand mess people up. Put your dx and tell me what you get.
4.995.
4.995, and we'll indicate units squared. And if this was a problem on the AP test, you'd want to show everything that I've shown here. So you'd show your graphs, you'd show how you got the intersection points, even though it's just writing this equation and putting the answer. They want to see that you solved this equation in some way. They'll know that if you put this as your answer, that you solved it using your graphing calculator, which is perfectly acceptable because it would be a calculator question. Then you show the integral that you integrated on your calculator, and then show your final answer. Good or no?
Good.
Wonderful. All right. Let's see. Okay. Time for some fun here. Let's see. Are we feeling okay? We feel like we kind of get the idea here. Look for the upper function, look for the lower function. And integrate,
Yeah.
right? I mean, find the points of intersection if you need to and integrate them. So now we're going to make things a little bit more complicated. So we're going to look for the area of the region that is only in the first quadrant, that is bounded above by y equals root x, and below by the line y equals x minus 2. So x minus 2, what does that look like? Looks like this, about, right? Do y'all agree with that? Everybody agree there? Square root x, y equals
Yeah.
x minus 2. Yeah, okay. We only want the region in the first quadrant though, which tells us that we are looking at this sort of weird little sector, right? We're looking at this section. And how is this region different from all the other regions that we've dealt with previously?
Because it's bounded by 3 lines.
Right, there are 3 different things that bound this region. The upper function is always square root of x. Would you agree?
Yeah, I would agree.
But the lower function is sometimes the x-axis, y equals 0, and it is sometimes the line y equals x minus 2. You all see that?
Yeah.
Okay, so what we're going to do is we're going to find this value where we switch from one lower bound to the other lower bound. So we need to figure out when does y equals x minus 2 cross through the x-axis. Well, when does y equals x minus 2 cross through the x-axis?
2.
When x equals 2.
Sorry if somebody's already said it, the trash is going by and my front door is just sitting wide open. So I can't hear you very well. Give me 1 second till the trash truck finishes doing its thing. Okay. Yes, x equals 2. Wonderful. So it crosses through at x equals 2. So from 0 to 2, our integral should be square root of x minus the lower bound, which is just 0. So we don't even need to put that, right? It's just the area between square root of x and the x-axis. But the second piece of it will have to be an integral from 2 to wherever these 2 functions intersect. Where do those 2 functions, where does square root of x intersect with x minus 2? Should be at x equals
4.
x equals. So we're going to integrate from 2 to 4, and this time it should be the upper function square root of x minus the lower function x minus 2 dx. Everybody good with that setup for this?
Yeah, it looks good.
All right, great. So let's find that area. What's the integral of root x, or x to the 1/2?
2/3 x to the 3/2.
So we got 2/3 x to the 3/2, evaluated from 0 to 2, plus, and once again, the integral of root x is 2/3 x to the 3/2. And then minus x will be minus x squared over 2, and minus -2 is plus 2, so that will become plus 2x. And we'll have to do that from 2 to 4. Good or no?
Good.
Okay.
Good.
Spectacular. Now it's just a matter of some unpleasant arithmetic. So let's see here. What do we end up with? We end up with 2/3 of 2 to the 3/2. What's 2 to the 3/2?
2 root 2.
2 root 2, right? So we have 2/3 of 2 root 2, so that'd be 4 root 2 over 3 minus 0, and then plus, if I evaluate 2/3 x to the 3/2 at 4, the square root of 4 is 2, and 2 cubed is 8, so that's going to become plus 16 thirds. Minus 4 squared is 16 over 2, so minus 8, plus 2 times 4, so plus 8. And minus, well, this is going to become the same thing we had before, right? 2 thirds x to the 3 halves at 2 was 4 root 2 over 3. Minus, this is 4, and this is plus 4. Everybody agree with that?
Yep.
Okay. Oh, sorry, that's not a 4. I made it.
And that's a 2, right?
That's 2, yeah. I forgot to divide by the 2. Sorry. Okay. So now let's look at what we got. We've got 4 root 2 over 3 minus 0. We can ignore the minus 0. We got the minus 8 and the plus 8. Those are going to cancel each other out, right? And then I've got a minus 4 root 2 over 3. So this positive 4 root 2 over 3 and this minus 4 root 2 over 3 are going to cancel each other out. And so what I'm left with is 16 thirds minus 2, right? And what does that give us?
10 thirds.
And thirds units squared. Everybody good with that?
Wait, is it not plus 2 because it's like minus 2 plus 4? It's plus 2, 16 thirds plus 2, or am I missing something?
You're missing this minus sign right here.
Okay.
Minus positive.
Okay.
Good or no?
Yep.
Fairly unpleasant, but could be worse, right? Much more convenient when the upper and the bottom pieces are the same function the whole time, not when they're different. All right, let's look at this problem. Oh, wait. This problem is the same problem, isn't it? True? But we still want this same region. Okay? So if I still want this same region, but I want to try and do this a different way. What if, instead of cutting it off here into the first quadrant, I allowed myself to find this whole area in blue and then just subtract it off this blue piece? Could I do that? The blue piece that's below the red line?
Sure.
All right. So what would the integral for the blue piece be? It would be an integral from 0 to 4, right? Because now my entire region has the same upper and lower, so I can do the full region, 0 to 4. What's the upper function? It should be square root of x. And the lower function should be what?
X minus 2.
And that's going to be all this in blue, but I need to take into account this. Well, what is this? This is a
Triangle.
triangle. Minus 1/2 the base times the height. Well, what's the base?
2.
And what's the height?
2.
So that should make life a little bit easier, shouldn't it?
Hopefully.
I hope so. All right, so let's take a look here. Now I've just got one integral to complete. Integral of root x is 2 thirds x to the 3 halves minus x squared over 2. And then minus negative 2 is plus 2, so that becomes again a plus 2x. And this time all we have to do is evaluate that from 0 to 4 and then subtract 2 to get our final answer. Everybody see that this should get us the same thing?
When you
Yeah.
when you originally set up your integral from 0 to 4 of square root x minus 2, aren't you already accounting for that small area when you do the integral of x minus 2, or like why do you have to add in the area?
So I'm getting this area, but I don't want this area. I only want the part in red.
So instead of like subtracting the integral of x minus 2, you're just doing the triangle formula.
Right. We could, if you wanted to, we could do this as minus the integral of x minus 2 from 0 to 2.
Okay.
But that's, you know, well, actually, we'd have to do plus it because it's below the x-axis. But yeah, that'll come out to be -2.
Okay.
Since it's a geometric shape that we know, we can just find that area and subtract it off.
Sounds good.
Okay, cool. So let's evaluate 2/3 x to the 3/2 for 4. Well, like we did before, that's 2 cubed is 8 times 2/3 is 16/3. And then -8 and then +8. Minus all of this evaluated at 0 is all 0. And then -2. So we end up with 16/3 -2, which is 10/3 units squared. And I feel like that was a little bit easier, right? So if we can find a way to use a geometric shape to break it up, great, go for it. If not, then you're gonna have to do it this way. Good or no?
Good.
Good.
Okay, now what about this one? Oh, wait. Oh, I didn't like that drawing. Oh, wait. I didn't like that either. Oh, wait. It's the same one.
Nice.
Anybody see a good way to go about doing this one?
Could you just do the integral of 0 to 4 of square root x minus 2 dx minus the integral of like from 0 to 2 of x minus 2, like subtract the overall one from the negative value down there.
Well, that's what we just did, right? Except we just used the geometric formula to find it.
Okay.
Integral of 2 to 4 of x minus 2.
And the integral from 2 to 4 of x minus 2 would just be this, right? But I want this in red.
So it'd be the integral from 0 to 4 of root x. Then
I just did the
minus,
integral from 0 to 4 of root x dx. That would give me all of this plus this. And what is this?
be the integral from 2 to 4 of x minus 2.
True. Or what else is it? It's just a
triangle.
Or it's just a triangle, right? And that makes life easier. It's just a triangle, I think. Right. So we could just subtract 1/2 the base, which is 2, times the height, which is 2, from it. And what do we end up with? We end up with this time just 2/3 x to the 3/2 from 0 to 4 minus 2. And as we've done multiple times, 2/3 x to the 3/2 evaluated at 4 is 16/3 minus 0. And we plug in 0 minus 2. Once again gives us 10/3 units squared. So we should see that there are a lot of different ways sometimes to complete the same integral. Isn't that cool?
If you like integrals, yeah.
Which you do, because you decided to take this class. All right. Any questions on any of those ways that we have integrated this so far?
Can you explain one more time why the second and third things we just did are different?
Are different from each other, you mean?
Yeah.
Yeah, so this one, we're taking the integral of root x from 0 to 4, which is finding this whole thing that I've shaded in blue. And then we've taken off this little triangle here, right, which happens to have a base of 2 and a height of 2. This one we found the integral between, or we found the area between root x and x minus 2 from 0 to 4. So we found this, and then took off this triangle on the bottom. So effectively, we're doing a very similar thing, but the integrals that we've used each time, like this original integral, found a different section than the original integral here.
Got it. Thanks.
That makes sense, sir. Cool. All right. I think that is a good place for us to stop today. Any other questions on that before I turn off the notes screen here?